I have a two-part presentation. The first part is to talk with new material that I've just put together about what the oceans can mean to us, or do mean to us. And then the second part will be we work within the oceans to actually begin to understand how they have become and will remain the life support system for pretty much the entire planet. So that's basically where I'm headed with the talk. So we'll see how it works. This is a famous statement, really, by John F. Kennedy. All of us have in our veins the same exact percentage of salt in our blood that exists in the ocean, and therefore we have salt in our blood, our sweat, and our tears. We are tied to the ocean. When we go back to the sea, whether it's to sail it or watch it, we are going back from whence we came, and that seems to be absolutely true. Many people feel bonded to the ocean in ways that sometimes they don't even understand. With that in mind, talking to the public in general about the oceans is exciting when you talk about the science, and that's because I'm a scientist, but it strikes me that it's not always the entire story. And so I began looking at how one could teach a course at the University of Washington. This is the arc of the course. We start with the origins of the ocean. The feeling is that it's not all about science because we are not all scientists, and the ocean means a great deal to all of us. And so looking at the spectrum, we go through all those topics, and we end with going off planet, which is the way I will end my presentation today. You're all familiar with the Vitruvian Man, who was actually sketched, and some people think it was a self-sketch by Leonardo da Vinci. And in it, he represents the proportions of the human body compared to nature. And it's Vitruvian because Vitruvio was an architect, and he used the measurements of the human body in what he built. So it also has become a cornerstone of Leonardo's attempts to relate man to nature, and I'll come back to that as we go on here. You may have also heard of the Fibonacci series, and it's really quite simple in a way, and I wanted to sort of point out, you start with 1, and you add 1, and then you add, and you get 2, then you add 1 to 2, and you get 3, you add 2 to 3, and you get 5, you add 3 to 5, and you get 8. And then you plot them in this fashion, and you get this beautiful spiral called the Fibonacci spiral. And the Fibonacci spiral is simply beautiful itself, but it's also maybe tied to some things. Let's look at how one might think about it. The global ocean and human culture, those are themes that I find really fascinating now. It's not just about the science, it's about the global ocean and how it's affected human culture for a long time. So it's the relationship between humans, hence the Vitruvian Man, and we'll see how the Fibonacci series plays out in terms of its spiral. There's the Fibonacci spiral coming in, and there we're looking at how human beings, that is the Vitruvian Man approach, how do human beings actually interact with the global ocean? Well, they work through all of these topics in one way or another, and many more, for sure. But let's just touch on a few of them. Many of them I'm sure you know about, but let's just touch on a few. For example, these have been in the news a great deal, and it's a beautiful spiral, but look how perfectly it matches the spiral of a shell. It's so beautiful. And so what is it about this Fibonacci series? Is there something there, something we need to know more about? It's something for us to think about and to spend time musing on. So let's go to the stewardship and the ethics and the arts and the entertainment. The ocean's role in our future. It hosts the Earth's largest ecosystem. It dominates the influence on the global climate. It has a growing role as a source of essential living and non-living resources, so we're depending more and more on resources that come from the ocean. Coastal regions are home to most of the world's population. The open seas are key to global trade and communications and security. The U.S., North America, has been saved from many, many wars, partly because we have oceans on both sides. Also, it is a major source of natural hazards, and therefore we have to keep a sharp eye on it. And increasingly, it's affected by human actions, which include CO2 emissions. So in terms of ethics and in terms of how we are stewards of the ocean, we must look after the ocean because it looks after us. It's that simple. Now, going to art. This is a beautiful painting the title of it is Gulf Stream. It's by Winslow Homer. And Winslow Homer painted this and called it the Gulf Stream, not knowing about the next picture I'm about to show you, which came from Benjamin Franklin, who worked in a shipping office in Philadelphia and began looking at the times that it took ships to come from Europe to the United States, or at that time to the colonies, and found that it took longer for the ships coming this way than it did for the ships going the other way. And he mapped that out, and he came up in 1786 with the Gulf Stream and mapped out this river. So there's art and science, and here is one of the loveliest ladies that's ever graced oceanography. Silent Spring, Rachel Carson, by all means read this. This is really excellent. And she's been accused of waxing poetic about the ocean. She says, if there's poetry in my book about the sea, it is not because I deliberately put it there, but because no one can write truthfully about the sea and leave out the poetry. So the arts and the science and our concerns. We talk about science and education. Let's take that one. Here is somebody's picture, a painting, basically, from Don Dixon, of what the early Earth might have looked like, but I'll superimpose on it some references and some paintings and photographs at the bottom of what natural scenes look like. But the bottom line is that through processes we still do not understand very well, the RNA contributed to the genetic code and the DNA of life, and that is what represents our ancestors. We are of the ocean not just because of the salt, but because life almost certainly originated within the ocean. How about religion? Well, how far back do you go with religion? This is Venus or Aphrodite emerging from the sea. It's a painting by an Italian painter, and this is something probably most of you are familiar with. I haven't met the man myself, but I really would like to see this done again. I think it would be really very cool, but it has a vaguely religious overtone for everybody except the Egyptians. And then the Hawaiians and the Polynesians in general had all sorts of gods and goddesses that came from the sea, and this is a particular location in Hawaii where people quietly leave offerings to their gods or goddesses. And it's just a wonderful, spontaneous component of Hawaiian life. Trade and commerce, let's just look briefly at. Here are the kinds of things that enter into the economy of the ocean. So I'm making the case that the ocean isn't just about science, and it isn't just about surfing, and it isn't just about any single thing. It's about all of these things. And the economy of the ocean is linked to all of these topical things. The offshore oil and gas deposits, they're the most valuable. Mineral deposits, they haven't begun mining these earnestly yet, but they probably will soon. Wind farms, ocean surface shipping is a big deal. Submarine cables at the bottom of the ocean, that's a big deal. Surface ocean shipping, bottom ocean communication. Wind farms, that'll be. And wave farms, I should have left that in. Shipwrecks and pirates, there's a whole set of stories about pirates. And then pollution. So many of these have economic impacts, and they're all related to the ocean. So, and then I said I would talk a little bit about warfare. Now, it's maybe hard to see what this is exactly. What it is a ship with a bowsprit here that is, or a ram, basically, made out of bronze, and it has crashed through this other ship. This is how naval warfare was conducted in the time of the Greeks. And it was a bad time, I got to tell you. And then the other things people began thinking about were pretty grim types of things. One of them is Greek fire. And somewhere around the 6th or 7th century, the Byzantines began routinely using this in naval battles, and it had something to do with naphtha, and it was almost as dangerous to use as it was to be on the receiving end. The bad part about being on the receiving end is you couldn't put it out. If you put water on this burning material, it just kept on burning. And so the only way to put it out was with sand. And at sea, you don't have buckets of sand very often. And then the ultimate force projection, I suppose, on the planet today is the nuclear submarine. So each of these topical things are ways in which humans interact with the ocean. So there's a lot of facets to the ocean, some of which are artistic, some of which are scientific, some of which are cultural. So here then is the beginning of the second lecture. The next generation ocean exploration, it has to do with how we begin to understand our own planet and as a life support system. First of all, though, let's establish that when scientists begin studying any particular kind of feature, they usually define what the system is. And here we have the system, and the system basically is the planet. And the challenge that we have is basically to optimize the benefits and mitigate the risks of living on a planet that is really driven by only two major energy sources: winds, waves, tides, currents. All of it, including photosynthesis and carbon cycling, are all largely driven by the energy that comes from the solar source, and it impinges on the top of the ocean and has maximum effect in the upper part of the ocean. There's another part that's near and dear to the hearts of geologists, and my specialty is underwater volcanoes. Internal energy works from below the ocean, and it's responsible for all of these processes. One other thing that I want to point out here is that in addition to all of these processes which you've heard about, the chemosynthesis is something that happens well below the depth of penetration of seawater. You may have heard about it from others. So then, in addition to those two energy sources, there is the human element, and human activities have begun to alter the Earth, or the ocean particularly, increasing its vulnerability to change. And the only solution that any of us can really come up with in any serious way, in addition to living more carefully thought through lives, would be to understand how the marine ecosystems actually function. But the bottom line here is the global ocean is the essential life support system of the entire planet. It provides 50% or more of the oxygen you breathe, absorbs greenhouse gases, it moderates the heat, it does many, many things. There's more heat in the upper 2 meters of the ocean, the layer that's only 2 meters thick, more heat in that layer than there is in all of the atmosphere. All sorts of things are actually conducted via and through the ocean. And therefore, the oceans are on both sides of that equation. You always hear people saying, well, never mind the environment, we've got to make the economy boom. And other people say, well, the economy, if the environment goes somewhere in a handbasket, then it won't matter how good the economy is, and it'll go down. The truth of the matter is, all your life and all the life of your grandchildren will be dealing with that balance. That's what we need to find, is the balance between environmentally responsible and sustainable things to do and an economy that is good for everybody that's involved. And those two things have to be done by people who don't dismiss the other side. They have to engage the other side and come to closure on what the best paths forward are. As a consequence, we need to balance all of these linkages, both the economic and the environmental, for the well-being of everybody. But the truth is, we're not that good at it. At first, you might say, well, maybe the folks that are interested in profit and making a lot of money they don't care much about the environment. Let's think about that for a minute. But a fellow from here in the late 80s and early 90s, Jeremy Jackson, actually pointed out that the ocean, a lot of the ecosystems were in serious trouble. And he was roundly criticized by a number of his colleagues. But it turns out that the magazine, The Economist, in the May 27 issue of this year, published a piece on the oceans. And this is one of the figures that they used. And they had a conclusion they came to, and their conclusion was the ocean sustains humanity, and humanity treats it with contempt. Now, that's quite an accusation. We don't want that to be true. And the beauty of what I'm sharing with you isn't that everything's fine, but it's that the most powerful magazine and influential magazine with regard to the economic side of things is recognizing that the environmental side of things is in real trouble. This is a wonderful step forward in my view. So then, the crucial focus has to be on marine ecosystem. The complexity requires that we enter the oceans from within and we begin studying them in totally new ways. The processes shown here are only about 10% of the processes that operate in the upper ocean. So that means there's probably something like 150 different processes that operate all the time, in addition to there being life distributed through the ocean. And so it's a very complicated system because it's been around for at least 4 billion years, and humans don't understand it very well because we are not very comfortable being there continuously. But that's what we have to do, and that's my argument. All of these processes operate all the time, and they interoperate, and that's what I'm coming to. If you have some mathematical leanings, you may either look up or know what n factorial is. N factorial, if n were 3, n factorial would be 3 times 2 times 1. But if n is 150, you can start now and be finished calculating what n factorial is sometime next week. Send me a note when you do. But that's proportional to the complexity of the ocean. That's my point. All of the processes interact with one another. So change one, you change the others. Therefore, it's very complicated. You're very fortunate to be living near Scripps Institution of Oceanography, which is an outstanding research organization. And they started something that was brilliant. They started it here. It was called the Argo Program. And it may be that you all know about it. I won't beat you to death over what it is, but I will show you what it is, because it is truly one of the more innovative approaches to oceanography. And one of the challenges oceanographers have is to be in the ocean all the time and understand how the ocean is functioning. And by taking these profiling floats, these gentlemen that I'm about to introduce you to, Russ Davis in the back and Dean Remick in front, they started this program with a brilliantly designed piece of hardware. The simple point is that it was a bladder that was inside and was connected to another bladder that was outside, and by changing the amount of oil in that bladder so that the size of the whole thing could increase or decrease by pumping the oil back and forth, they could make this measuring device go up or down compared to the density of the ocean. It's just brilliant. And it started around the 1990s, late 1990s, and look where they are today. There are well over 3,800 plus of these units all over the ocean, and they go down about 1,000 meters, they hang out, then they drop down to 2,000, and then they come straight up measuring properties of the water all the way up. It's just brilliant. And here is a measure, the kind of scientific measure that we all like to see. Those are publications on the right-hand side there. Those are, it's a very, very successful program, and you should be very proud that it started right here in your backyard. And not to be out of the game entirely, but Seattle billionaire Paul Allen bankrolled a small addition which allows some of these elements to go even deeper. After that, there became an entire program called gliders, and I won't go into the glider story right now, but think of it as one of these floats that goes up and down, but it has wings on it, and you can count the wings. And so it could move, come to the surface, and then could dive, and you could tune it so that it would go off in one direction or another. And that, too, was dominated by a lot of the folks that work here at Scripps. Many groups around the country are using gliders. So let me then just step sideways and say the emphasis here is on being in the ocean all the time, 24/7, 365 for literally generations. And the beauty of what they're doing is that they crack that nut very early on in a comprehensive four-dimensional way. They're in the ocean all the time. The thing that we wanted to add, and we will soon add, is we also want to be able to be communicating in real time with many of the instruments that are out there and make them do what we want when we want them to do what we want. And that's because hurricanes come, big volcanoes erupt, earthquakes take place. There are many, many things that happen in the ocean that you want to be able to go over to and study, and you can't get a ship there in time. But the main point now is that we're on the threshold of what you're about to see next, and that is a vision of next generation science. The streams coming into that pool are all the data streams from all over the world coming into a huge pool. They're all streams from different kinds of data, different data streams coming from all over the world about the oceans. And they flow into an ever-expanding reservoir, which contains historical data, and therefore you can always compare the historical data that are in the archive or the reservoir with whatever the real data is coming in real time. So let me share with you then the thing that I've been involved in, and that is an example of launching a different type of sustained approach to long-term interactive human presence within the entire ocean. And the National Science Foundation put forward a program that was called the Ocean Observatories Initiative, and it began in 2009 and was completed in about 2015-16 and is operating now. 2 sites in the southern hemisphere, 4 sites in the northern hemisphere. The one that I'm associated with is the one here. All of these others are linked by satellites. So the data rate is fairly slow going through the satellite. The one that I'm involved in is the one that has fiber optic cables. This square is that square. Fiber optic cables that come from shore and go out across the Juan de Fuca tectonic plate. My backyard underwater is the Juan de Fuca tectonic plate. So let's look at something else that's even bigger. I talked to you about the global planet, but now let me talk to you about the global volcano. Starting in Iceland, all the way around, it's 70,000 kilometers long, goes all the way around the world like the strings on a baseball, the stitches on a baseball, and it's 70,000 kilometers long, and it's probably erupting somewhere all the time. In fact, maybe erupting many places all the time. And it is a place where the seafloor pulls apart at about the speed your fingernails grow, anywhere from 3 to 8 centimeters a year. And that's, geologically, that's a lot. And from deep below, the hot part of the Earth, molten rock rises into that opening and creates lava that flows out on the floor of the ocean. And about 70% of all the volcanism on the planet takes place in systems like this, underwater, out of sight, but not out of mind. And for you, you'll always remember that now, I think, for the rest of your lives. Well, now, why did I go there after introducing you to the Juan de Fuca tectonic plate? Well, here's why. What I'm about to introduce you to then is a verbal rendering of an animation, and what this thing does is turn on its axis, and you see the Juan de Fuca Ridge, just like it's shown here, just off the coast of Washington, Oregon, and then we go down, 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 under the water, and we see this next figure, which is axial seamount. There's the Juan de Fuca Ridge coming right through. Axial seamount is only 1,500 meters deep. There's a picture of it there. This is axial seamount in all of its glory. And here is what axial seamount did. What you see, that little square there, or that little rectangle, is the caldera of axial seamount, and you can see it there in that inset as well. But what you also see in orange is a cable. It's a fiber optic cable. It's about, in this case, 514 kilometers long, and it comes from Pacific City on the Oregon coast all the way out to the other side of the tectonic plate, up on top of the volcano, and the little red box near the top of the volcano is called primary node 3B, and it is right on top of the volcano. And the volcano is known because it erupted 3 times in the last 2 decades. We expect it to erupt again in about 2 to 3 to 4 years. So just to give you background, this is Vancouver Island here. This is the Explorer plate. It's a little plate. This is the Juan de Fuca plate here, and we're going to go down that one. But over here is a line of seamounts, just like the ones coming off of Hawaii, except these are smaller. And it joins the ridge crest, the Juan de Fuca Ridge, right here. So let's see what that looks like. Yeah, there we go. The Juan de Fuca plate, or the Juan de Fuca Ridge is right there, and there is where the seamount chain hits, and that's where axial seamount is located. And if you have any interest in going and looking at that, just search on the Pacific Marine Environmental Lab of NOAA, and they have a page that's devoted to that. Now, I'm going to take you below the seafloor. So these are seismic profiles, these gray things, and they're being inserted into the map of axial seamount. So there's the caldera in the top. You see the caldera? And this is what the magma chamber down below looks like. The seismic penetration to the magma chamber is very different from the rest of the rock. So we're able to identify where the molten rock is below the seafloor. That's the caldera again. And we're going to go down and look at the magma chamber. And this is the part that is most full of molten rock, liquid lava. And over here, it's got more crystals in it. And then we're going to simulate in an animation an eruption to the surface, but I'm then going to show you the real data. What you're about to see is an animation of the volcanic output on the seafloor, and we mapped this in great detail using autonomous underwater vehicles. So that is the lava flow that actually came out during the 2011 eruption. So this is really pretty exciting. And here is what a cutaway view of the same system looks like. There's the caldera, there's the magma chamber, and right there is where the lava flow that I just showed you is. And so these are all structures, and this is all done by seismic imaging. It's very complicated to do. On top of that now, the part that I was involved in is putting this cable in place and this cable in place. And we have wired this part of the Juan de Fuca tectonic plate and ridge crest. And our Canadian colleagues have wired the northern end. We agreed that they would do this some years ago, back in 2000. So it's 900 kilometers, 10 gigabit per second bandwidth for this cable. Every one of these nodes can be served at 10 gigabit per second. And 8 kilowatts of power are available at each of those. So it's like an underwater substation in a way for both communication as well as power. Here's another quick view of axial seamount just to emphasize the primary node, which I'll show in the next slide, and we'll take you right in here. This is 3 kilometers by 7 kilometers. And here's a close-up of the caldera. There's the wall on the one side. There is PN3B, that's its primary node 3B, and that cable goes all the way to the Oregon coast right there. But these are all the instruments that are already in place out there, and they're all sending data back in real time. And the one that I'm going to show you is this one, the HD video camera, which is located right here, and it's trained on something that is called mushroom. Remember, mushroom is the structure that I'm going to show you. I won't show you right away because I had a workshop in Seattle on April 20th of 2015, and I got all my colleagues, 95 people from all across the country and Canada and Europe and Japan, to come to Seattle to talk about, well, what are we going to do now that we have this volcano wired and we think someday it's going to erupt? What would we do if it erupted? And we spent 3 days talking about it. It was really exciting. We had all kinds of plans of what to do, and by the time people got home the following day, on the 24th, the volcano erupted. What's really cool is that we caught, the very first second we knew that something was going on. In fact, we knew there was a buildup. There were more and more earthquakes, and then this cluster came, and then all of a sudden it went right through the roof. In a very short period of time, about 18 hours, this happened, and then look over here, this little part here is expanded, so you can see it drops off to almost nothing. That's what you're seeing here. So after the eruption, the earthquakes went away. So what we're talking about is molten rock from below the sea floor coming from deep, deep in the earth has been rising and rising and rising and filling that magma chamber I just showed you, expanding the magma chamber and making the rocks above it crack and crack and crack and crack and crack until eventually it reached critical stage and one crack too big, one crack too many opened, and the magma came rushing on through out onto the seafloor. And this happened on the 24th of April. I wish I had scheduled the workshop the day after instead of the day before. But let's take a look then. Over here, you have the caldera. You're familiar with the shape of the caldera now. And what you're doing is looking at the earthquake patterns. And there's the timeline. That's 2015. That's March 10. And those are the hours ticking off over there. Well, it erupted. Let me show you what else happened in addition to the earthquake. All the cluster earthquake all happened within about 18 hours. And here is the 18-hour period, right? That right there, from there to there. The seafloor in the middle of the caldera dropped almost 2.5 meters, and I'm about a little over 2 meters tall. So that's how much the seafloor dropped because the magma went somewhere else. And then the temperature of the water inside the caldera went up almost a degree, which is very, very unusual, as far as we know, because we've never been there before. But previously, we got out there in about 3 weeks, and we didn't see this. This time, we couldn't get out there for almost 3.5 to 4 weeks. That was a real problem. Now, there's more to this story, but I want you to listen to something, so I'm about to go with the sound that an erupting underwater volcano makes. These are not earthquakes. These are the sounds that it makes when the lava comes out on the seafloor, and we think it's explosions. And these are recordings during the eruption, which we were then able to locate by having different hydrophones in different locations. And we used the hydrophone location to triangulate on where the events were. And they were not in the caldera where the lava, some of the lava came out. They were way up the way. So this is in the lower left. You see all the blue dots? That was the earthquake. And then for a month afterwards, the red dots, which were the explosions, took place and took place and took place and took place. So somewhere, a lava flow formed here, and then there, and then there, and then there, and then there. We were able to use the locations of these hydrophones and the seismometers to pick up where those explosions were. So we went up there later. It was about 4 months later. We got up there, and there was a lava flow that had come out that was so high that it was almost two-thirds, maybe almost, well, it's two-thirds the height of the Space Needle. It's about 400 feet high. Really surprised. We didn't know that. Now, here is what we think is going to happen next, and that is, here's the first eruption, and then it took a long time. Then the second eruption, 2011, and the seafloor dropped again. And then this is the one that I just showed you. And then it dropped again. And now it's climbing again, and we think if it goes on that slope, it's going to erupt next year. If it goes on a very different slope, similar to that slope, it's going to erupt somewhere in 2024. So this is what we've begun doing. Think of it this way. Anything that you're interested in that changes offshore rapidly could be addressed with a system like this if you have the fiber optic cable and you have the power and you have the sensors in place. Anything you want to look at. Whale migration patterns, fish stock assessment, big earthquakes or big eruptions, big plumes coming offshore, all sorts of things that take place. Now, I want to go to what I talked to you about a minute ago and share with you my favorite quote by Marcel Proust. Real voyage of discovery consists not in seeking new landscapes necessarily, but having new ways of seeing things, new eyes. And here is the eye that I mentioned to you. It's in the caldera. This is the structure, and on the right-hand side there is the mushroom structure. It's about 14 feet high. And that little box there, this is the camera. The camera is right there, and these are the camera lights on either side. These are the batteries. And there's the cable going off to Oregon coastline. But this is what you're looking at. You're looking close up. See that little black unit there? That's this thing. And it's a rock that's growing, and in another 20 minutes to 5 hours, it's going to fall, and then it's going to grow again. The rocks grow out there. like they're like the weeds of a hydrothermal system. But that's iron pyrite, chalcopyrite, zinc, a mineral called sphalerite, and it has some gypsum, or kind of anhydrite, which is a form of gypsum. And this is bacterial, some of these things on the edge. So that water is around 250 degrees centigrade. So it's really, really hot water. Whereas out here away from it, the water is only 2 degrees centigrade. So there's very steep gradients right there. Okay, another close-up of the same thing. I just showed you this. Shows some of you, if you're interested in the animals, I don't want to beat that to death, but there's the camera here on the edge of the caldera. And here is a crude rendering of the thing. And what I'm going to show you next is a time series of high-definition imagery from November 2015 to July 2016, one frame every 3 hours. So we have been taking the video. What you're going to find is that this chimney grows and falls and grows and falls and grows and falls, and it almost does it to the music. Those are rocks growing and falling. These are all the animals. They're moving around all the time. This is the cooler part over here. This is warmer. And over on this side, it's really, really hot. And this is the bottom. This is how ore deposits form, it turns out. But that box I showed you earlier, right here, that you can see, that's the whole structure. Here it's expanded. We have very high resolution video. And I'm going to show you a little box inside that's expanded in the next graphic. But see, look at the resolution. These things here are smaller than half of my fingernail. And that's how well we're seeing them. Things like, those are limpets. And you'll see those in the next picture. So you can see this is amazing imagery from 400 kilometers offshore on top of an active volcano, showing you life that lives on chemosynthesis, not photosynthesis. This is 1.5 kilometers deep below sea level. And here, 2 weeks ago, here in town, over on the campus at a group called Qualcomm, I worked with Larry Smarr and a couple others over there. And these are the images. There's Larry. You can see he's a normal-sized human. Okay, and so this is 4 panels high and 8 panels wide. These are big panels. And we had data coming live. We controlled it from there. So what I'd like to try to do is set that up here so that folks from here can actually watch live displays on a volcano that's about 700 kilometers away from here. It's the only part of the mid-ocean ridge, that 70,000 kilometer long piece, it's the only part that's ever been wired underwater and continuously sending data. Here is the caldera. Here I'm rendering the eruption, and we never saw this. We never got out there to see this. What I showed you was a black smoker, or hot water coming out of the seafloor, but I didn't show you this because we never got there. And this is what's in there. It rises almost a kilometer above the seafloor. It sometimes is as much as 20 kilometers across, maybe 30 sometimes, the big plume, and it carries novel microbes that nobody's ever seen before from below the seafloor. Somehow we have to detect and quantitatively characterize a mid-ocean ridge, MOR, mid-ocean ridge eruption, because there's 70,000 kilometers of mid-ocean ridges. And this is the idea that my colleague and I, Dana Manalang, have come up with. And it's a robot that we can control from land through these kind of communications. And that's the Acoustic Gateway. That's the cable that goes ashore right there. And this is a docking station. That's one of them going into the dock. There's one up in the water column, and that's another one that's mapping the seafloor here. This is called a resident AUV system. We're gonna have It's like a self-driving car for underwater, and we're going to put it offshore, and we're going to give it a little garage that it can run into, and it can download data and upload power to charge its batteries. That's the plan. And here is the caldera again. That's the lava flow from 2011. Here are the lava flows from 2015. So obviously, we need something that can move around at least 15, 20 kilometers in the area in order to fully characterize where the hot water rises up into the overlying ocean, because that is what goes on at mid-ocean ridges all over the planet all the time for the last hundreds of millions of years, probably billions of years. And this is what we imagine happening, is having something like this. So this is a dream, just like the cable out there is a dream. We hope to have this within another 3 years. And so there's the plume, and it rises and it spreads. And there's the lava flow on the seafloor, and there is one of the vehicles. There's another one, and there's another one. So we will have robots that do what we tell them out there, and we communicate with them every day and a half when they come in to download power and upload data. And we can reprogram them on the fly. There is a finite possibility that within the next 100 years, there will be a magnitude 9 earthquake on the subduction zone there. And we want to extend the cable, which is currently here. That's what I already showed you. We want to extend it here. We want to extend it down there. And we want to be able to anticipate the first movement of the earthquake as well as the first movement of the tsunami. And the Japanese are doing this to the tune of about $1 billion off their shore. We think we can do it for only 300 million, and it's a real deal. So, I'm shifting gears now. How many of you know who Wayne Gretzky is? Okay. If he were an oceanographer, would oceanography win the Stanley Cup? What does that mean? That seems a little cryptic. Well, the truth is, people ask him, how come you're so good? And this was his answer. Skate to where the puck is going, not where it is now. Now, why do I bring that up in a group like this? Well, the answer, the reason, is very simple. We've been through one industrial revolution, which was the 18th and 19th century. There's another industrial revolution that took place in the 1870s, and there's electrification of the countryside. There's another revolution that took place beginning in the 1980s. Many of you remember that for sure. And it involved digital representation, changing from analog to digital. It's still going on. But many people, including Klaus Schwab, who's referenced at the bottom there, think we're in the middle or the very beginning of the fourth industrial revolution, which builds on the digital revolution in new ways. Tech becomes embedded in society and in the human body. Artificial intelligence, nanotech, robotics, biotech, Internet of Things, 3D printing, and autonomous vehicles. Okay, so all of those things are within our reach. We're at the beginning of this revolution. And here's what Klaus has to say. The possibilities of billions of people connected by mobile devices with unprecedented processing power, storage capacity, and access to knowledge are unlimited. And these possibilities will be multiplied by emerging technology breakthroughs in fields such as artificial intelligence, robotics, the Internet of Things, autonomous vehicles, 3D printing, nanotechnology, biotechnology, material science, energy storage, and quantum computing. Okay, maybe he's right, but let's just look. You all know about Moore's law. All right, Moore's law is, Gordon Moore noticed in the 60s that the number of circuits that could be put onto a particular chip doubled about every 18 to 24 months. So if we take 18 to 24 months and we start at year 1 here, this is what year 2 would be like in terms of the capability. That's year 3, year 4, year 5, and year 6. By the end of 5 years, since we started at 1, it's 32 times more capable than it was when it started. Well, that's impressive, but not nearly as impressive as if you look at it from 10 years. Then you go from 1 here all the way up to 1,000 in 10 years. That's what we're faced with if we have exponential growth in the capabilities of computers or sensor packages or communications. I mean, the fiber optic cables have followed this curve precisely. So there are many, many things that are in this category. Now, is this the limit? No. Take a look at genomic sequencing. That's Moore's law in green, but starting at $100 million in 2001, when I believe all of you were alive then, somewhere in 2007 there was a major change, and now you can sequence an entire genome for less than $1,000. This is profound. It's not only profound because it happened, it's profound because it's going to keep happening. And all of you are going to be affected powerfully by this process, particularly you young folks. Imagine running out 50 years. So what might the future of ocean exploration involve? Well, it's going to involve all of these things. Broad spectrum, evolving sensor capability. We'll have the ability to do almost anything. Tens of thousands of highly intelligent, artificial intelligent, adaptive platforms, that is, underwater robots, operating at many different scales. The scale of a blue whale to the scale of a copepod or a shrimp. Real-time communications, and that's one you should challenge me on, and in-situ auto repair and replication. These things, because of the nanotech artificial intelligence combine, will be able to take carbon from the water and build the carbon fibers that break or get injured while they're offshore. This is a new way of starting to think about the future. This is really quite different. So the strategy is to take maximum advantage of the rapid convergence of all those things I've talked to you about. And here, you can think of it this way. There's the genomic area of influence. There is the nanotech area of influence. And there is the artificial intelligence area of influence. Where they overlap, including communications, which I couldn't show very easily here, is where marine robotics will be 10, 12, 14, 8 years from now, well within all your lifetimes. And this was done for me by one of my illustrators, the guy that does my illustrations. You have to admit, he's pretty good. But he threw this at me at the last minute, and this is a robot made out of carbon fiber. And it actually works, and this is what we're going to be deploying in the ocean. Eventually, we will pick up on what is actually out there, and we will mimic, or it'll be biomimicry, we will mimic creatures that have worked in the ocean for hundreds of millions of years and know how to move from one place to another. But not all of them are going to be strictly organic. In fact, what I've begun to do is call these not robots, but organobots. So be careful when you buy salmon 10 years from now. Be careful to check and see if it has any sensors in it. All right, so something happens. How would we use this? Something happens in the ocean, and we decide that there's an area that is dominated by diatoms, the base of the food chain. And we have these robots that can move around, and they can measure something that we call the meta-genome of that volume of ocean. And so they go about and they measure it, and that's kind of rendering the meta-genome. There is no such thing as a meta-genome. It's a term used by Craig Venter, but I'm using it loosely to characterize that volume which is underlain by diatoms. Then you have one that's underlain by coccolithophores. And the coccolithophores hold up a different kind of ecosystem, and the robots, when they get there, can recognize the difference. They map out another kind of genome. So think what we're doing. We're using robots that are artificially intelligent that can move through entire volumes of the ocean, and they can map out the boundaries between adjacent ecosystems. So suddenly we are in a position to begin understanding much more so the complexity of underwater systems, even though they are constantly and dynamically changing. And then, of course, just because I'm a volcanologist, I had to have an erupting volcano in here somewhere. And it would have its own genome. So we are then mapping metagenomic domains, volumes offshore. Now, the question you then begin to ask, well, where will the puck be in a field that's dominated by exponentially changing technologies? And this is something all of you should be asking, particularly you young folks. Well, it turns out there are pucks, and there are pucks. And this man, this man was brilliant. He fascinates me. I've read everything he's written. He says, sometimes I think we're alone in the universe, and sometimes I think we're not. In either case, the idea is quite staggering. At least 3 people were staggered. The rest of you are just laughing. All right. So let's look at Europa. Those blister marks on the ice, the icy surface of Europa, which is the second moon of Jupiter, and the cracks, that's all in ice. But the ice is very thin, only about 1 to 10 kilometers. But the water layer on Europa is huge. It's 100 kilometers deep. We don't have anything on this planet. All we have is 11 kilometers in the Marianas Trench. So let's use our imaginations and go below the surface. And we think that there's volcanoes underneath because the next satellite closer to Jupiter is Io, and it is the most volcanically active body in the whole solar system. So this is its nearest neighbor. This is Europa. And we think there's volcanoes on the bottom. And my colleague, John Barras, thinks that life may require plate tectonics in order to get off the ground. You have to have the right kinds of things. And there's another group that has just finished off the Cassini mission. This is Saturn. And there is Enceladus. Usually I have it circled. Here's Enceladus. And that's part of the E-ring, by the way. This whole thing is E-rings. These are well-organized rings. This is a poorly organized ring because all the material that's in it is coming out of Enceladus, that tiny little dot. But this is what it looks like. Cassini imaging scientists used views like this one to help them identify source locations of individual jets spurting ice particles, water vapor, and trace organic compounds from the surface of Saturn's moon, Enceladus. That's an actual picture. All right, I'm going to end with the poem by Matsuo Basho, which is part of the book that he wrote, the most incredible book he wrote, which is Oku no Hosamichi. And if you get a chance to read it, it's not on most of the bookshelves, but you can get it. You can get it. It's not the one that's published in 1689. That's when he wrote it. But try to get a hold of it because he talks about his interaction with reality. And he juxtaposes here, for your consideration, or anyone's consideration who cares for haiku poetry, the ocean is turbulent, and yet the sky is clear. So the ocean is turbulent because of a big storm, but the big storm has passed, and he sees the Milky Way. But what he's also juxtaposing is this ocean here with the vast number of potential oceans in solar systems and beyond in our galaxy and beyond our galaxy. The potential for going off-planet in ways that I hope most of you kids that are here from the high schools will be part of. I believe the adventures that we are facing us, both in terms of technological development and exploring at least the nearby galaxy, are absolutely profound.